Dear friends, today we will discuss about the Heisenberg uncertainty principle. You know, the very popular expression delta x delta p greater than h cross by 2. That means the minimum value of delta x delta p is h cross by 2. What is delta x? Some uncertainty in the position. And what is delta p? Uncertainty in the momentum. So this principle explains that there is a minimum value for the product of uncertainties of these two measurements like position and momentum, as well as like energy and time. So there is, minimum value which is h cross by 2. It may be greater and of any value, there's no problem. But minimum is h cross by 2 and will not be lesser than that, this uncertainty. Now, this is not a statement about the inaccuracy of the measurements, measuring instruments or the measurement instruments. Okay, so remember, keep in mind, it is not inaccuracy of our measurement, and nor it is a reflection on the quality of the experimental methods. And it is very important to remember that it arises from the wave property. Wave property is inherent, which is inherent in the quantum mechanical description of the nature. It is inherent property of the wave nature. Even you are having very perfect instruments and techniques, the uncertainty will always be there because it is inherent in the nature of the things. Okay, and more often we give a statement, like we give one statement which is not correct. And what is that statement? The particle has a position and momentum. But if you get quite detailed information about the position by doing some measurement, then you can only get vague information about the momentum. This statement oftenly we give, but it's a wrong statement. Think over it. And second statement, which we use as a proof of uncertainty principle, that statement is again a wrong. And what is that? To find the particle position, then you bombard it with the light. But to make more precise position measurement, you need that light to have very small wavelength. And what the de Broglie hypothesis, okay, lambda is equals to h upon p. So if the lambda is very less, it means it has high momentum, and high momentum to give some to particle. When we give to some particle, and now there will be uncertain about the particle's momentum, because you are imparting a momentum to the particle. Then how you will measure the momentum? How you say that's the correct momentum of the particle when you measure it, when you're measuring it? This statement we oftenly give to explain the uncertainty principle. But it is again a wrong statement, because it seems that there is somewhat inaccuracy in our measurement. But remember always, there is nothing concerned with the measuring method. There is nothing concerned. Okay. Let's that when you proceed downward in size, okay, to the atomic dimensions, then it is no longer valid to consider a particle like a hard sphere, okay, because the smaller the dimensions, the more wave-like it becomes. It no longer makes sense to say that you have precisely determined both the position and momentum of such a particle, because particle is no longer there. When we are going in a very small dimensions, then the classical particle disappears, and what appears, that is a wave. When you say that the electron acts like a wave, then wave is the mechanical, quantum mechanical wave function, and is therefore related to the probability of finding the electron at any point in the space. We would try to find classic, like we are having a wave, probability wave, and we try to find out there where our classical particle will be in that wave packet. So to explain all this, that the duality, okay, or the uncertainty, Heisenberg uncertainty, it is not in the something wrong in the measuring instruments. So that's why the error comes like delta x and delta px. It is the inherent property which will exist how much we make the very good instruments even then. So we consider a perfect sine wave, let's for example, and that the electron wave that spreads, okay, spreads in the space. And if I have a single sine wave, then its probability also spread throughout the space, throughout all the space. And the position of the electron then becomes completely uncertain, because the probability wave is spreading in this whole space. So position of the electron becomes uncertain, but there will be certainty in the momentum, because only one wave having a single value of lambda. So there will be a single value of the momentum, but the position becomes quite uncertain. So let's accompany with me for this topic. Okay. This is a sine wave, having a unique value of the wavelength. Like you know very well, the distance between the two crests or the two trough, that is called the wavelength, lambda. If the lambda is having a unique value, that means it implies that momentum is precisely known. Momentum is very precise in this case, unique value of the momentum. This wave is extending from the left side as well as from the right side in the space. And if you find the probability, okay, if you find the probability of this wave, then that probability also spreads over all of the space. And what is the probability? Psi star psi. The probability it spread all over the space, then it is very difficult to tell where the particle is. It is existing all of the space. mean that uncertainty in the position is almost infinite in the position. But momentum is having a unique value in this case. So delta P is certain, but delta X is totally uncertain, right? So position is now adding the several waves of the different wavelengths together will produce an interference pattern which begins to localize the particle. You know how? Look, low frequency, slightly high, and this frequency is slightly greater than the previous. This frequency is still slightly more, and this frequency is slightly greater than the previous one. So we are having a number of waves which differs by wavelength in a very small amount or frequency in a very small amount. If these waves they interfere, okay, or you apply the principle of superposition, then you will get a wave packet of this shape. Then you will get a wave packet of this shape. So what is there? A continuous distribution of the wavelengths. So the different type of wavelength produces a localized wave packet. What happens? The result, it is a wave packet. And now you notice the amplitude of the wave packet is maximum here, and it gone decreasing along this side and ultimately almost becomes zero here, and it is decreasing along this side and approximately it becomes zero at here. That means the particle can be localized between these 2 points. So delta X now becomes certain. Okay, the delta X, it is there. Well, the position is certain within delta X. Finding the particle position is within the delta X. So wider spread of wavelengths when there is a superposition of large number of wavelengths, then contributes a smaller value of uncertainty in position. Then we can localize the particle within the delta X. If you go on increasing the number of waves, delta X becomes smaller and smaller. But there is a drawback also. And what is that? Every different wavelength represents a different value of the momentum, because momentum is h over lambda. So if there are large number of lambdas, mean there is a large number of momentas. If there is very large number of momentas, so then finding the momentum, the true momentum of the wave packet becomes almost very difficult, very uncertain. Okay, delta P, I mean to say, the problem in P becomes large. So if delta X becomes small, delta P mean finding the momentum or the error in momentum, that becomes uncertain, that becomes large. Stress spreads. Now, you know very well, I just explained that the Heisenberg uncertainty principle, it is not there is no uncertainty in the experiments or there is no, you know, there is nothing any wrong. So this uncertainty principle. So this uncertainty is actually the inherent property of the wave itself. There is no problem of measurement. So let's we discuss this uncertainty principle again. This is Q. Along this side, it is a position, and along this side, it is the momentum. Now we are having a particle, and we are having a very, very precise instrument, very, very accurate instrument for measuring position and momentum. When we noted down the position and momentum, we are getting the dots here. When at one time, this is the value of position, this is the value of momentum. At the other time, this is the position of particle, and this is momentum. So this spread shows there is some error in the value of the position, which is delta x, and there is some error in P, which is delta P. It shows. Okay. Now, if for another group, for another group, for other particle, when we noted down the position and momentum, then we will get a spread like this. So what happened here? This spread shows the value of delta P, which is along y side. It decreases, whereas the spread in position delta x, it becomes large. So if delta P decreases, delta Q becomes large. Delta Q means position. Now if we have chosen again another particle, and we are repeating the experiment several times, so we are getting again a spread. This spread. Here we are quite certain about the position when delta x is small, but here delta P becomes very large. So if delta Q decreases, delta P increases. So this is what the Heisenberg uncertainty principle